Okay, we are going to talk about coordinate systems, trigonometry, and vectors. So, uh, let us just define a coordinate system as a grid on which you can locate an object. Now, right here is a two-dimensional coordinate system. A one-dimensional coordinate system would just be a number line, basically. And the position on a one-dimensional coordinate system would be 1, 2, 3, 4, 5, or -1, -2, -3. In two dimensions, in a plane, you have an x-axis and a y-axis, so a point can be defined by a x position and a y position. So this point is 5, 3. This point right here, the position is -3, 4. This position xy right there is something in between, maybe x equals 3, y equals 8.3 or something. Anyway, when we're going to talk about something in motion, it's very useful to be able to have some kind of frame of reference, and we're going to use a coordinate system to do that. We also need a grid like this to be able to determine things about not just motion, but how to look at the interaction between things. So again, here, this right here, sorry, that last part was a little vague. Don't worry what I just said. I'm doing this on the fly. Anyway, here is a coordinate system that is a polar coordinate system. Instead of talking about x position and y position, it talks about distance from the origin and angle from the reference line. So that's a polar coordinate system. Hopefully you've seen some of this in math. We will use this a little. Mostly we'll use the regular xy coordinate system. However, right now we want to just make sure we understand basic trigonometry. So if you have a right triangle, we can define 3 different trigonometric definitions. Each one of these has to do with a ratio of 2 of the sides of the triangle. So for example, sine of theta is just a number which is equal to the ratio of the side opposite to the angle and the hypotenuse of the triangle. So the sine of theta, if this is theta right here, is going to be the opposite side over the hypotenuse, so it'll be y over r. And it's just a numerical number. I mean, if this is y equals some value, and this is like 6, and this is 8, then the sine would be 6 over 8, which would be 0.75. I just made that up, but that's basically all it means. The cosine of an angle is going to be equal to the adjacent side divided by the hypotenuse, so it's x over r, and the tangent of theta is the opposite side over the adjacent side, so that's y over x. Now the thing that's really useful about these ratios is it doesn't matter how big your triangle is. If I make the triangle 3 times as big, these ratios of the sides are still exactly the same. So the sine, cosine, and tangent of a particular angle don't matter how big the triangle is, and that's a really useful thing. Now we're going to apply this in a minute to something called vectors. Oh, yeah, sorry. And you know the Pythagorean theorem that the squares of the sum of the squares of these two sides equals the square of the hypotenuse. Useful tool to have. Okay, and then if you have, say, the sine of the angle means the opposite of the hypotenuse ratio is 0.866, you can inverse it, and that gives you back, well, what angle gives you that ratio? And that angle will be 60 degrees. And if you have a tangent of something is 0.4, the inverse tangent means that the angle who gives you that xy ratio of 0.4 is 21.8 degrees. Okay? That is basic trig, and that's about the depth of which we'll use it for our purposes. Okay? Now we're going to talk about something called vectors. You may have heard of these back in 9th grade physics, but vectors are a type of quantity that have both an amount and also an associated direction. Scalars are a type of quantity that don't have any direction associated with them. So for example, mass is a scalar. There's no direction to mass, it's just an amount. Temperature is a scalar. It's an amount of, well, it's a measurement of the average kinetic energy or something like that of the molecules in something, but there's no directionality associated. Usually they write vectors with an arrow over it or maybe in a bold letter. We will probably sometimes get a little sloppy with it, but for example, v with an arrow over it would be velocity, which is a vector, versus v unbolded without an arrow is for speed, a scalar. They're very similar. We'll talk about the similarities and differences, but one is, the main issue is that one is a vector and one is a scalar. Okay. These vectors are all equal. They're all the same vector. A vector is represented in a diagram by an arrow, the direction of which is shown by some kind of reference, frame of reference or coordinate system, and the length is represented by the length of the arrow. So each one of these are oriented in the same direction, and they're the same length. They're all equal vectors. For example, a force acting on something in this direction is exactly identical to a force acting on something over here. Same thing, I should say, the same thing in the same direction. It's the same force applied in the same direction. If force is an example of a vector. Now, if I want to add vectors graphically, it's actually quite simple. If I want to add the vector a plus b, I can take the vector a and take the vector b. This is vector a, this is vector b. I take vector b and I place the tail of vector b at the arrow of vector a, and I place them in their proper angles. And if I draw a final vector that starts at the origin of the first vector and ends up at the termination of the second, this vector r equals a plus b. Now a plus b also equals b plus a. So if I added them in the opposite order, you can see I get the exact same thing. I can add a bunch of vectors together simultaneously. Here's a plus b plus c plus d. I use the same method, arrow to tail, tail to arrow, tail to arrow, tail to arrow. The final termination point and the origin point, a vector that goes from the beginning to the end point. That is, in fact, the sum of all those vectors. And an example of this would be a walking trip. Displacement is a vector quantity that is not the same as distance. Distance is the total length you travel, so you'd have to add just the arithmetic. This amount plus this amount plus this amount plus this amount would give you your distance traveled. But your displacement is a vector that represents your final position relative to your initial position, and that would be the sum of all those vectors. We'll talk about that more in an upcoming video. Okay? Subtracting vectors is basically a minus b is the same thing as a plus the vector negative b. The vector negative b is just the vector b reversed in direction. So if you have a plus b would be this vector like that. A minus b is you just take the vector b, flip it around, use the same adding method, tail to head, and so the vector a minus b would be this vector right here. So again, a minus b is the same thing as the vector a plus negative b. Okay. Multiplying a vector or dividing by a scalar, you just basically increase or decrease the length by the amount of the product or the division. Here's 3a, 3 times as long as a in the same direction. Minus 3a is 3 times as long as a, but in the opposite direction. Okay? Here's something for you to think about, come up with your answer. We'll discuss it in class. Minimum and maximum amount that any two vectors added together could be. Okay? So, I can also take a vector, because I know that vectors, this is going to be useful to us in a few weeks. We can take a vector and we can break it into subvectors. So here's vector A. I know that a vector this way plus a vector that way, here and here, those add up to equal vector A. So vector A right here is equal to vector ax plus vector ay. And if I make it 90-degree triangle, and I use my rules of trigonometry, I know that ax equals a cosine theta and ay equals a sine phi, as we'll see in just a second. Okay? So look, here's vector A. I could also break it up this way instead of putting ay over here and this over here. But ax plus ay equals a, and that's very convenient. I know the trig identities. Cosine theta is ax divided by a. So therefore, ax equals a cosine theta. Similarly, ay equals a sine theta, and tan theta equals ay over ax. Very convenient. Okay? And so a is the square root of ax squared plus ay squared, because we know the Pythagorean theorem, as we just discussed in the a few minutes ago. Okay? So this is going to be useful, because sometimes we don't want to just draw a picture of the vectors. We want to be able to add them numerically and trigonometrically and algebraically. Okay? This is just another diagram showing that this plus this is the same thing as that plus that. It's the exact same thing, just done basically on a different side of the triangle, and basically you could say in a different order if you want. Okay? But now, to add vectors algebraically, all we got to do for the final vector is get the x components of the subvectors and add them together to get the x component of the final vector. And then we do the same thing with the y vectors, and then we put them back together again, as we'll see. So here's two vectors. They're not at right angles to each other. You can add them together by breaking each into component parts. So look at vector A. You can break it into ax plus ay. You can take vector B. You can break it into bx and by. And so if I look at the final resultant vector C, which is drawn right here, we can see, if you look at this picture, that Cx, this component of C, is just equal to ax plus bx. This length plus that length, because when you add them parallel, you just add them. And so Cx equals ax plus bx. Cy, which is this vector right here, is equal to ay minus by, and you get cy. So I'm just going to put in some values for a and b, and then you can just piece it together and go back and see how it works. Basically, let's say vector A is 10 units, and it's an angle 50 degrees above the horizontal. And vector B is also 10 units, but it's at 20 degrees below the horizontal. Okay? So I can just calculate ax equals a cosine theta, just 10 cosine 50. I can get ay is a sine 50. And I do the same thing with bx. So then I get cx is going to be ax, this value, plus bx, this is this value. And if you do the numbers, you get 15.8. So cx is 15.8 to the right, which is the sum of ax and bx. And cy is going to be ay, actually it should be minus by, or plus, just to say minus by, because it's in the opposite direction, and you will get 4.2. So resultant vector is 15.8 this way, 4.2 that way, and I can then get the angle by using the Pythagorean theorem, and I can get the angle, I can get the length of the vector, I get the length of the vector by doing the Pythagorean theorem at 16.4, and an angle using the tangent, which is cy over cx, and that's going to be 14.9 degrees. So vector C is 16.4 units long, and this angle of 14.9 degrees above the horizontal. All righty, that is that.